Hi guys, I'm Dave. I work at a local startup here called PREDIKTO, local to Atlanta. We move unplanned maintenance to planned maintenance, so we do a lot of classification on heavy machinery, like what component will fail. I mainly work on a Python stack, but not too long ago, I was writing message brokers in Spring Boot, so I'm familiar with it. So real quick, what am I going to talk about? Real brief intro into TensorFlow. Just sort of go over the real thin basics. Then we're going to spend a lot of time coding, or at least I'm going to spend a lot of time coding. Then I'm going to go over like some pros and cons of what I've learned about putting TensorFlow with Spring Boot, and then we'll just sort of conclude from there, and it'll be open for questions. First things first, disclaimer: this is not a machine learning talk. If you guys came here to learn really cool linear algebra and do matrix math, this is not the talk for you. This is going to be really simple, high-level overview of connecting TensorFlow with Spring Boot. If you're looking for more in-depth stuff on machine learning, Andrew Ng, Jan LeCun, the Google Brain team, OpenAI, they got tons of great stuff out on their blogs and on YouTube talking about like how do these things actually work, how do artificial neural nets work. And in the second half, there will be memes, so look forward to that. What is TensorFlow? Who here has used TensorFlow? Okay, cool. So who here knows what a tensor is? Awesome. A tensor is just a really fancy name for a typed multidimensional array. So if you had an array of arrays, or an array of arrays of arrays, those would all be tensors. They would have rank 2 and 3 respectively. So TensorFlow is just a graph-based computational framework to process these tensors. Tensor's an input, and you have an output as a tensor. Some of these graphs can be fairly simple, so you'll notice on your right-hand side that there's a graph that looks like it takes some image bytes in, it decodes a JPEG, it does some pre-processing with the value and the mean, and then it'll finally spit out a tensor. Or they can be extremely complicated, like the one at the bottom. This is actually a graph or image representation of the graph called inception, which is what we'll be implementing today. The inception graph is a very specific architecture for how to connect these nodes in once again, like a really specific way to do image classification. In fact, this is state-of-the-art image classification right here. So this is all great. I know what, now I kind of have a feeling what TensorFlow is. I know what a tensor is. What does this help me do? This is becoming a really popular toolkit for people who want to do state-of-the-art image classification or audio synthesis or style transfer. So companies like Lyrebird and the app Prisma. Has anyone here used Prisma, the Prisma app? You guys? So let's take a look at what this stuff is. So this is Lyrebird. See if I can.
Hey, Doc, have you heard about this new technology?
Are you speaking about this new algorithm to copy voices?
Yes, it is developed by a startup called Lyrebird.
This is huge. They can make us say anything now, really anything.
The good news is that they will offer the technology to anyone.
This is huge. How does their technology work?
Hey guys, I think that they use deep learning and artificial neural networks.
Hillary is right, and I can tell you that their team is great.
I wish them good luck. I'm sure they will do a good job.
Hey, Doc.
All right, great. So that clearly was obviously not Barack Obama, Donald Trump, and Hillary Clinton, but it does sort of sound like them, right? And I mean, previously you guys remember Microsoft SAM? Like, it was terrible. This is way better than Microsoft SAM. I'd love it if Barack Obama told me, like, hey, you created a new file, like every time I created a new file on my laptop. That'd be awesome. So this is image style transfer. Someone took a picture of an arch. The neural net has learned, hey, I know what Starry Night by Van Gogh looks like. Let me apply the Starry Night style to this picture of an arch. And then you have an arch that was painted by Van Gogh. That's pretty cool. I think it's pretty cool. So artificial neural nets, and TensorFlow actually is very specifically used by Prisma because it's a Google app, are state of the art in these fields. So the people who want to build these sort of tools are using toolkit TensorFlow. All right, but I don't know how to build these tools. I don't know, how does this help? How does this help me as an enterprise developer? Well, actually, there's an API for Java. And the cool thing about all of the APIs is that if you build a graph, let's say in Python, and a data scientist trains it, feeds it a ton of input images and labels for those images, they can actually export that graph as just a plain file, and you can import it into your app using a completely different language, not have any knowledge of the construction of that graph, and run TensorFlow on top, like just run that tensor through it. Which means we can do that in Spring Boot. So let's get to some code. By the way, does anyone know what this is from? Anybody? Anyone here a Grey's Anatomy fan? Okay, just me. Great. That's good to know. So I sort of skeletoned out a lot of stuff, but we're gonna work together on the actual main TensorFlow code. So the first things first, what do I want this little microservice to do? Well, I'd like it to do one real big thing. I'd like it to take in a request that has an URL, and to prove to you that this URL is what I say it is. This is a picture of a grand piano. Can we all agree that this is definitely a picture of a grand piano? Great. I'm going to post this to /API image, and I would like back a label that says, hey, this is a grand piano, and the probability that it's a grand piano is 91.38%, or in this case, the float 0.9138. So as you can expect, the main code for the controller is fairly simple. We're going to take the URL, we're going to read it in as an image, and we're going to get the raw image bytes. Now, because we're expecting a JPEG, these bytes aren't particularly useful to us because JPEGs are a compressed image. So we're going to have to do some decoding, we're going to have to do some pre-processing on our side before we can actually run this through TensorFlow, because we really want, the RGB values from 0 to 255. We, separated them out to 3 different channels, et cetera, et cetera. And then we're going to execute the inception graph. So there's this little, there's this little inception runner that we need to build, which is going to hold most of our TensorFlow code. First things first, build a component. This is a little component. It auto-wires in some inception properties. The first main property is the location of that graph file. It's just a protobuf file. We couldn't even really open it because, is anyone here familiar with protobufs? Protobuf buffers? Yeah, it's a binary format for serializing objects. So reading it in a text editor is just going to be garbage, but it is a protobuf file. And we're going to also need going to need to read in our image labels. Let's go ahead and do that. And the labels in this case there's one line per label. So every line has a label. So what we can do is we can just open up a little Java stream, get everything line by line, and just collect it to a list, and return that list as the list of labels. Now, we're going to need to, remember I said, we're going to need to process those raw JPEG bytes into something usable that we can actually do some math on top of. And if you recall that there was that graph I showed earlier, which was this graph, we're going to want to read in the image bytes, decode a JPEG, we're going to resize it because all JPEGs aren't of the same size. We're going to get the raw values, we're going to get the mean values, we're going to do a subtract on them, and we're going to divide by a scale constant. In this scenario, we would imagine that our data scientists have told us, hey, This is the grand piano. We expect it to be a 91% probability. Before you take in any image and run it through our inception graph, you're going to need to do these 5, 6, whatever steps. And you're going to have to do that on your side. So let's just imagine for a moment our data scientist gave us the spec that they had maybe written in Python, and now we got to go ahead and run it in Java. So you can see we're going to read in the image bytes, and we're going to start a graph. And this is just the standard main object for all graphs in TensorFlow. It's just called graph. We're going to want the images scaled to 224 by 224. The mean value of RGB values is going to be the average from 0 to 255, which turns out to be the median as well, which is 117. The scale is 1. Let's just assume for a second our data scientists knew that dividing by 1 would give us the same number, but they're asking us to divide anyways. So let's just go ahead and do that. And you can see that there's this graph builder that's not there yet. This graph builder is actually going to give us all of the operations that we're going to need to do the pre-processing. Decoding the JPEG, resizing the image, adding any constants that we may need, doing a cast. So let's go ahead and build this graph builder. So first things first, it's going to take in a graph as its only constructor arg. And we're going to need to want to add operations to this. And the majority of our operations are going to be binary operations. So in the case of a subtraction, x minus y, our binary operation is subtract x minus y. And that's going to be a common pattern for us. So let's go ahead and build a little helper function for it. And you can see that the first thing we're going to do is on that graph that we input as our main constructor arg, we're going to add this op builder. An op builder is basically add an operation, a specific operation of the string, of the name that you give it, to the graph in question. Then we're going to add in an input. So we're going to add in x. We're going to add in y. We're going to build this operation, and we're going to get the very first output of it. That's good. So now we have a helper function to build binary ops. Let's go ahead and build our first binary op, which is the division. So we're going to obviously take in an x and a y. And this output type is sort of like the intermediate type between having a tensor and not having a tensor in TensorFlow. We pass in that the operation we want is div. So the way that you use in the Java, you build and get operations in the Java API is you actually have to pass the name of the operation as a string into the op builder. So in this case, we want to do a division between x and y. Remember, we also have to do a subtraction, so let's go ahead and do a subtract. It's the same pattern. We're going to do sub x and y. We're also going to need to resize the image. Remember that all images are not going to be the same size, so let's go ahead and do a resize. In this case, we're going to use resize bilinear. Bilinear resizing is a really, really common technique for resizing JPEG images. If you've ever played around with Photoshop, there's different options for resizing it. And I believe the default one, at least last time I played with Photoshop, which was on the desktop, so it was a while ago, was resize bilinear. And this is, of course, another binary op. We're going to take in the images that we want to resize, and we're going to give it a size. And we'll see how to use this one specifically in a moment. We're also going to need to actually decode our JPEG, so let's go ahead and do that. And we're not going to use a binary op for this because the number of channels that we want, which in this case in a JPEG, channels are the red values, the green values, the blue values, and if there is an alpha channel, which is the transparency layer of an image, we might want that. But in this case, we're probably not going to want that because transparency is probably not going to tell us a lot of information about the content of an image. So because it's not a binary operation, we're going to have to go ahead and do another op builder. In this case, we're going to give it decode JPEG. We're going to add an input as the image content. So in this case, it's going to be our bytes. And we're going to set an attribute. So attributes are set for some functions. Attributes are sort of like an input parameter into the actual, not necessarily an input parameter, but like a field member of the actual function decode JPEG. So in this case, we're going to tell it how many channels we actually want it to decode. And we're going to do the same thing. We're going to build the operation, and we're going to get the first output of that operation. RGB values traditionally are 0 to 255, and they're usually ints. And because we're going to do floating point math, we probably want all of our values to be floats to begin with. So we're going to want to do a cast. And you can't just do this as a cast in TensorFlow. You actually have to run an operation for it. So we're going to do something very similar to decode JPEG. We're going to give it a cast operation. The input value we want to cast, and then the data type. This data type is a built-in TensorFlow object that has a bunch of static members on it. You look, data type, there's float, there's int, et cetera, et cetera. And we're going to go ahead and build and get the first output. Our data scientists also told us, hey, we trained a lot of these images in batch. So sometimes you're going to want to add an extra dimension. You're going to want to add what TensorFlow calls a batch dimension. And what batch means is just what you would traditionally expect, like in Spring Batch. We might want to process more than one image at a time. We might want to batch it up in 10 or 15 images at a time. And the reason TensorFlow has that option is because TensorFlow can run on graphics cards, which we can parallelize heavily on graphics cards when we're doing this sort of mathematics. GPUs lend themselves really, really well to this sort of math. So they told us, hey, you're going to need a batch dimension for the inception graph that we handed you. So there's an expand dimensions function. It's just going to be another binary op. Finally, we're going to want to add constants, because like our scale constant that we are going to use to do the division, the image might actually be a constant that we keep constant as a sort of input into the whole tensor, or TensorFlow graph. So in this case, first thing we're going to do is we're just going to take in an object, and the name that we want to name is constant, and we're going to try to create a tensor out of it. If this doesn't work, obviously it's going to throw an exception, and the whole thing is going to blow up. There's another operation called the constant operation in TensorFlow. Are you guys noticing a pattern that everything is an op builder with a name and a type? Just kind of remember that, because we're gonna come back to that and discuss why this is the way it is. We're going to set an attribute, which is the data type. We're going to set an attribute, which is the actual value of the tensor, and then we're going to build an output. So we have, I think everything we need to actually go ahead and write a little helper function that does a resize of the image. So we're going to have to read this in to out, because it gets a little hairy at times. We're going to decode our JPEG to 3 channels. We're going to cast that output from an output of type int32 or int64 to float. We're going to add a batch dimension, and then we're going to finally resize the image. And luckily, because we have a constant helper, we can actually add the size as a constant, which is what resize bilinear is going to look for. And we're just going to make height and width into a tensor that is the constant of the size. Cool. So now we can resize the image. Now we're going to have to preprocess it. And if anyone ever really wanted operator overloading, now is the time to really want it in Java. At least this is what I felt. We're going to resize the image, and then we're going to preprocess it. So let's read this once again, in from out. We're going to do a subtraction of the value minus the mean, which is another constant that is an input. And then we're going to do a division by another constant called scale. And then we're going to return that as the preprocessed image. Cool, so finally we can preprocess an image. Let's go ahead and finish preprocessing this image and output as a tensor. So we're going to use that little preprocess image helper. We're going to give it the input, which is this image bytes that we converted from a constant byte array. So now we have a little output, that intermediate object. We input that. We input the height, the width, the mean, and the scale. And now we got back a graph that we can run to convert those image bytes into a tensor. So the way we run graphs is with a session. We start a new session. The session takes in the graph that we want to run for that session. Then we get the op name for the graph that we just built. And we fetch and run that operation, and we get the first output. And that's what we need to do to get a tensor for that image. So now we have a tensor that we can run through TensorFlow. Let's go ahead and run TensorFlow. Now, I know this doesn't look like much, but this is probably the most powerful 8 lines of machine learning code I've seen after just doing a simple linear regression. This is pretty cool stuff right here. We're going to convert that image to a tensor. Remember, an output of TensorFlow is also a tensor. So we're going to get the label probabilities. The inception graph that we imported earlier, we're going to start a session up for it. We're going to feed in the input image. We're going to fetch the output. Now this stuff, our data scientists have told us, hey, when we built this graph, these are the inputs and outputs that we expected, and this is how they were named. We're going to run it, and we're going to get the very first output, which is going to be the list of label probabilities. Tensors aren't particularly easy to iterate through or inspect without using a bunch of their helper methods. So what we can do is we can copy those label probabilities to a float array, and that'll be a lot nicer for us to look through, find out which of the label probabilities is the highest, so we can give our users, hey, this is the label probability and this is the label associated with it. So we copy that, and then we need to do a get labels. So get labels is just going to iterate through that float, or that float array, find the max, find the index of the max, and build a little prediction response with the label. Remember, we did 1 line per label, and they were in order that the tensor would output it also, which is really nice for us. If it wasn't in that order, this would not work. And then the probability that it was that image. And that's it. Let's run this test and see if it works. Hooray, it works. So we have image classification in 159 lines of code. I think that's pretty impressive. So what are some pros and cons here? Well, there's a growing community. This is really cool stuff. TensorFlow is getting really widely used by people who write a lot of machine learning software, by data scientists, and there's a lot of growth on the Python side of things. And it's easy for these guys to use. They aren't hardcore developers or anything like that. They're just they're working with numbers most of the time. Unfortunately, the con is that every other API is auto-generated from C++ code. So if you're not a Python developer, you're stuck using auto-generated code from C++ API, which is not the easiest thing to use because, as you can tell, we have to know what the names of these operations are, and we have to know what they do. And you can't just look for them as a class, right? There's not a cast class or an operations class that has a cast function on it. You have to just know the name that it was named in C++, which isn't great. I don't think it's great. Which also means all the documentation is auto-generated from C++ code, which makes it hard to understand. And all the comments and all of that stuff is auto-generated from C++ code, which gets really tough at times. So looking for a list of these operations, you either have to go to the Python API, or you have to look through C++ code and find their names and find all the attribute names to figure out how to use the Java API. And finally, the worst thing, because it's C++ code, it's all JNI. Which means if you're going to debug, has anyone ever here tried to debug JNI code? Okay. For those of you who have never done it, I want you to go try to do it. What ends up happening is because these are native objects, who here is familiar with what JNI is, first of all? So for those of you who aren't familiar, JNI is the Java native interface, and it allows Java to talk to C, C++ code, basically compiled binaries like .so files. Because those are native and they aren't happening, those calls aren't happening within the JVM, you can't inspect it with a debugger because they can't look inside of those memory locations. Which means if you have a bug, let's say, in the dimension of your array for TensorFlow, good luck, because you can't debug it in IntelliJ. And those three things I think are pretty bad. But I think it's, it's still pretty cool. And TensorFlow can clearly do some neat and interesting stuff. We saw Wirebird, we did image classification locally. We saw Prisma. Prisma is a really cool app. Prisma is actually using TensorFlow under the covers locally on Android, which is all Java anyways, right? But it's probably not ready for the primetime enterprise setting, right? Without good documentation and an easy way to figure out what operations to build, this is probably not tenable in a production environment. But doing it for fun and figuring out new ways to integrate this, you can imagine, like, let's say you had a Slack bot, and every time someone posted an image, a Slack bot just said, hey, I think this image is blank. Eventually, you're going to get some interesting responses, because if it sees an image it's never seen before, like, let's say it's only ever been trained on dogs and cats, and suddenly it sees, let's say, a ferret, it's going to freak out. It's going to just say ferrets or cats all day long. That's going to be, I think that's going to be pretty funny to just see fill up in a chat window. And because there's a growing community, there's hope that more people will write documentation, and that Google, who runs Android, which is all Java, will invest more heavily. So the future is bright in my eyes. I see a lot of potential for TensorFlow doing really cool image classification and speech classification. And that's it. Thanks. This is my contact info, and I think we have plenty of time for questions. Yes, I think we have like 10 minutes for questions. So does anyone have any questions? Yes. No, I haven't, because if I'm just going to write Jython, at that point I might as well just use the great Python libraries that TensorFlow has. TensorFlow has tons of really cool Python libraries. They have one that looks like scikit-learn. They have Keras. They just wrote a new one that's for reinforcement learning. That one got released yesterday. So I know I haven't tried it with Jython, but I can't really see a use case, because even if you are going to write it in Jython, if you write it in Python, you actually can debug the tensors and all of that stuff, because the way Python works with C, it actually can look inside those memory locations. So it ends up being a little nicer if you just do it with Python then. Any other questions? Yes. I'm sorry. Oh, yeah. So I actually haven't looked into the stats, like what kind of throughput you could get. Potentially, if you had the right hardware and the right setup, let's say you had TensorFlow compiled for a GPU and you had a big GPU cluster and you were running all these services in parallel, you could probably get pretty high throughput, because those GPUs are super, super fast running these artificial neural networks. But I don't know, I don't have any stats off the top of my head about what sort of rate. It took maybe a second or so locally, and this is not compiled with any sort of optimization. So I would say you probably could do, easily get an image a second. But yeah, I don't have any hard numbers to back that up. That's just a guess from experience. Any other questions? Bueller? Bueller? All right, guys. Thanks. This was a lot of fun. I appreciate it. Good day.